Hey, there we go. So can everybody see my slide that says balancing chemical equations? And you see some of my writing on here too? I didn't take the time to erase it. Okay, thanks, Anthony. Appreciate that. Great. Well, let's get started. And, the last shall be first, right? This is where we ended off the last lecture, which was last Thursday night. We stopped right here. We talked about balancing chemical equations. And I went over these rules with you. And we went over an example. And I'm not going to go over this specific example again, but I want to go over the rules with you one more time before we tackle some more problems. So rule number one, when we're trying to balance chemical equations. And before we get into rule number one, let me just say something that from now on in this class, from this moment forward, whenever you see any chemical equation, whether it's in the lecture or in the lab, on an exam, in a homework, wherever you see it, you should always ask yourself, is this equation balanced? And if it's not, you should balance it yourself. Okay, there you go. All right, so something to think of, or something to think about. Always balance your chemical equations. So first, you're going to write the correct formulas for the reactants on the left side and the correct formulas for the products on the right side. Now, in order for you to write correct formulas, you've got to know nomenclature, right? Step number two, you're going to change the numbers in the front of the formulas. Those are the coefficients, right? You see the equation we balanced last class. 2, 7, 4, 6. Those are the coefficients, right? Those are numbers that we can manipulate. We cannot change the subscripts. That's cheating, right? If I was to take H2O and I needed twice as many hydrogens and I put H4O in there, there's no such thing. It doesn't exist. So you can't change the subscripts. Next, you're going to start by balancing the elements that appear in only one reactant and one product. Balance the elements that appear in two or more reactants and products, and make sure you have the same number and type of atom on both sides of the equation. So you can always check your work. Now, the way that I would do this is, I think the easiest way is whenever you have any element by itself, like here you have oxygen all alone, whenever you have any element by itself, I would always save that for the very last, and that will be kind of your, ace up your sleeve. All right, so let's take a look at an example here. It says, when aluminum metal is exposed to air, a protective layer of aluminum oxide, Al2O3, forms on its surface. This thin layer prevents further reaction between aluminum and oxygen, and it is the reason that aluminum beverage cans do not corrode. In the case of iron, the rust or iron 3 oxide that forms is too porous to protect the iron metal underneath, so rusting continues. All we're asked to do here is a lot of preamble for this question, which is write a balanced equation for the formation of aluminum oxide. So we want to form Al2O3. And we want to form some Al2O3. And we want to write a balanced equation that shows the formation of Al2O3. Well, if we're forming a protective layer of Al2O3 on the surface, that tells us that the Al2O3 is a solid. And when something is a solid, we denote that by putting S in brackets. So this is Al2O3 solid. Well, what two elements are in aluminum oxide? Hopefully you can see that it's aluminum and oxygen. Well, let's start with aluminum. If I go over to my periodic table, so I got my periodic table here, I look at aluminum. It's in group 3A, it's element number 13. And aluminum simply exists as Al. Now, what do you think the phase of aluminum is in its natural state? Do you think that's a solid, liquid, or a gas? Aluminum, based on your knowledge. Based on what's in the problem, right? It's a solid. It even tells us, okay? It tells you that when aluminum metal is exposed to air, okay, if something's a metal, it's going to be a solid. The only exception to that would be mercury, okay? So we have aluminum that's a solid, and we're going to add that to oxygen. Now, oxygen is one of the diatomic elements. In the videos that I posted for chapter 2, I went over all nomenclature, and you have to memorize the diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You have to memorize that all of these elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they all come in packets of 2. Okay, that's just something you've got to have in your brain. So that means that our oxygen is going to be O2, and oxygen is a gas. Now we just need to balance everything out. Well, if we have 2 aluminums in the product, in aluminum oxide, we're going to put a 2 in front of here. And if we have 3 oxygens in aluminum oxide, but there's O2, who could tell me something times 2 equals 3? What is this something? Can anybody tell me what that would be? What times 2 gives you $3? You know, how many dollars do you have to double to get $3? Exactly. It's one. It's
Yeah, you can.
1.5. Right? You can either put 1.5 or we'll put it as a fraction. We'll put 3 over 2 like that. So now my equation is perfectly balanced. The only thing we're going to do is we're going to eliminate the fraction. So in order to eliminate this denominator, we're going to multiply the entire thing by 2. And when we do that, we get 4 aluminum in the solid phase plus 3 oxygen in the gaseous phase gives us 2 molecules, or 2 formula units, I should say, of aluminum oxide. Like that. So there's our balanced equation. Give me a thumbs up if you're like, you know what, Mr. Dion, give me a little bit of time, and I think I could balance an equation. All right. Okay, great. Well, let's move on. But before we do that, I just want to talk about this, and I mentioned this last class, is that a common mistake that you'll see in general chemistry is students will try to relate coefficients, the numbers that I'm highlighting, the 4, the 3, the 2, they'll try to relate those coefficients directly to masses. Okay, now don't write this down because it's wrong, very wrong. They'll say, okay, well, if I have 4 grams of aluminum, then it's going to react with 3 grams of oxygen, and it's going to give me 2 grams of this, of aluminum oxide. That is, there's no such thing. Okay, the coefficients do not represent masses. The coefficients represent respective number of moles. So any general chemistry textbook basically any general chemistry textbook on planet Earth, if you open up any book, if you go to the library, find an old book, if you buy one on eBay or Craigslist, whatever, you're always going to find some version of this figure in any general chemistry textbook. And what they're saying is if you have a reaction, okay, and let's just make something simple. If we have A, going to B like this, if you were given a mass in grams of A, okay, in order for you to compare that to grams of B, what you would have to do is you have to convert that to moles of A, and then you do a conversion between moles of A and moles of B using your balanced equation. Then you can convert the number of moles of B to the grams of B. And what you really cannot do is this. You cannot compare grams like this. This is a big no-no. So going back and forth here, no, no, no. You cannot do that. Okay? And that is why you have to have a balanced equation, because your coefficients have to be correct in order to get the correct relationship or ratio of moles of reactants and products, right? Now, how do we convert masses of substances into moles? We use molar mass in grams per mole. How do we do that? We go to the periodic table. We calculate it if we have to, okay? And then finally, once we do a conversion from moles to moles, then we can go back to grams again. So it's a steppy process, right? You got to do 1, 2, 3 steps. And again, a knee-jerk reaction for some students, not you guys, but is to try to convert grams to grams, and we cannot do that. Well, let's look at an example where we apply that. It says here the food we eat is degraded or broken down in our bodies to provide energy for growth and function, right? You form ATP. A general overall equation for this very complex process represents the degradation of glucose to carbon dioxide and water. If 856 grams of glucose is consumed by a person over a certain period, what is the mass of carbon dioxide produced? Well, the first thing is that we don't have a balanced equation, do we? If you look at the equation here, we have 6 atoms of carbon, but only 1 over here, right? You can see there's a bunch of problems. So let's rewrite that equation, and let's start by balancing it out. So I'm going to rewrite it here. We're going to do C6H12O6 plus O2 gives us CO2 plus water, like that. Now watch. When I told you about balancing equations, I said it last lecture and I said it at the beginning tonight. I said whenever you have any element by itself, you save that, we're going to save the O2 for last. Always save anything by itself for last, because you can put any number on Earth in front of that. okay, to get what you want. So let's start out. Look, we've got 6 carbons here, but we've only got 1 here. Now 1 times what gives me 6? The answer is 6. I've got 12 hydrogens here, but I've got 2 here. What times 2 gives me 12? The answer, again, is 6. Now, let's tally up all of the oxygens that are on this side. Can anybody tell me how many total oxygens are represented in the products right now? Total. Exactly. It's 18, right? I have 6 times 2, right? So I have 12 from the carbon dioxide, and I have 6 times 1. So that's plus 6. So that gives me, I have 18 oxygens over here. 18 oxygens, okay? Well, here I have 6, and I need to have 18 on this side. So if I have 18 minus 6 from my glucose, that gives me 12, and I have 2 right here. What times 2 gives me 12? The answer is 6. So now everything is perfectly balanced out. Don't believe or balanced out. Don't believe me? Check. Okay, so this is a perfectly balanced equation right here. C6H12O6 plus 6 moles of O2 produces 6 moles of carbon dioxide and 6 moles of water. Give me a thumbs up if you think you can balance that equation. Like, give me a little practice, Mr. Dion, and I'll be able to nail that. All right, and then we can try some stoichiometry. Okay, good. Well, let's rewrite that equation. I'll just write it here. We have our C6H12O6 plus 6 moles of oxygen gives us 6 moles of carbon dioxide plus 6 moles of water. There's our balanced equation. Now let's solve the actual problem. It says we're starting it with 856 grams of C6H12O6. That's glucose. Now we're trying to figure out the mass of CO2 produced. We know that the ratio of moles is for every 1 mole of glucose that's consumed or degraded, we make 6 moles of carbon dioxide. So that means we need to figure out how many moles of glucose we have. Well, we can find the molar mass of glucose, C6H12O6. I've gone over this in detail in class, how to do that. You add up the molar masses of 1 carbon, 12 hydrogens, and 6 oxygens, and you get roughly 180 grams per mole. Okay, and we're also going to need the mass of carbon dioxide because we're looking for that, and we get 44.01 grams per mole. Okay, so we're going to need those to solve the problem. Let's get back to it. If I want to figure out the number of moles of glucose that I'm going to get from 856 grams, I'm going to need to use my molar mass and divide by that molar mass. 180 grams of C6H12O6 is found in 1 mole of C6H12O6, like that. Now I'm going to convert the number of moles of glucose into the number of moles of carbon dioxide. Watch, my mass of glucose cancels, and I use my balanced equation right here. I know that for every 1 mole of C6H12O6 that's consumed, I could produce 6 moles of CO2, right? This conversion factor here comes from balanced equation, okay? From balanced equation. All right. Now again, if I was to stop here, all I would have is the moles of carbon dioxide, but I want the mass of carbon dioxide. So I'm going to say in every 1 mole of carbon dioxide, I've got 44.01 grams of carbon dioxide. There we go. All my conversion factors work out. When I punch all that spinach into my calculator, 856 divided by 180, multiplied by 6, multiplied by 44.01. We get an answer. I'll just throw this out there to my students. Can anybody tell me how many significant figures I should have in my final answer? And there's 3 sig figs in the 80 or 180 grams per mole. Can anybody tell me how many? Yes, I should have 3. Right, there should be 3 sig figs. I have 3 here. I have 3 here. All the molar conversions, those stoichiometric coefficients, those are absolute, or those are exact numbers. Right, those have an infinite number of sig figs. And I have 4 in my molar mass of carbon dioxide. So when I put that in my calculator, I get 1.25 times 10 to the 3 grams, like that. Okay, so that's the mass. If you want to convert it to kilograms, divide by 1,000. So if you take your calculator, and you should know how to use the exponent function, 1.25 times 10 to the power of 3 divided by 1,000 gives you 1.25 kilograms. Okay, either answer is perfectly fine. Okay, now this is a very typical type of problem that you'll have on your next exam and the final exam as well. So let's take a look at another problem that's very similar to that one. All right, oops, I didn't mean to do that. There we go. Here we are, right here. Okay, so this problem here says, and all alkali metals react with water to produce hydrogen gas in the corresponding alkali metal hydroxide. What are the alkali metals? Could anybody tell me what group the alkali metals are found in? This is just some review.
1A.
Yeah, it's group 1A, exactly. Group 1A, perfect. So the alkali metals react with water to produce hydrogen gas and this corresponding metal hydroxide. A typical reaction between lithium and water is shown here. Got a problem because it's not balanced, is it? Anyhow, it says how many grams of lithium are needed to make 9.89 grams of hydrogen? Well, the first thing that we need to do is we need to balance out the equation. So let's rewrite it. So we have lithium plus H2O, and I'm leaving the phases of matter out. You can include them. I'm leaving them out because I'm just trying to balance the equation. Anyhow, here we go. We've got, look, we've got one lithium here. We got one lithium here. No problem there. We've got one oxygen here, and we've got one oxygen here. Hey, it's all good. Over here we have two hydrogens, but over here we have 1, 2, 3. Well, remember what I told you. If you have any element by itself, you can manipulate that so that you can balance it any way you want. Now, if I only need 3, why don't I just put a half in front of this, right? If I have 1/2 times 2, that equals 1, right? The 2's cancel. And so I have 2 hydrogens over here, and now I have 2 hydrogens over here total, right? So now my equation is balanced. If you want to eliminate the fractions, you multiply the whole thing by 2, and you would get 2 lithiums plus 2 moles of water produces 2 moles of lithium hydroxide plus H2, like that. There you go. We have a perfectly balanced equation. All right. Well, let's start out with what we know. And all we're given is that we have 9.89 grams of hydrogen. So let's write that down. We have 9.89 grams of H2. What's the molar mass of H2? If you take the molar mass of hydrogen, which is around 1.01, and you multiply it by 2, you get 2.02 grams per mole. But remember, and I'm repeating myself here, we're starting out with the number of moles, or grams of hydrogen rather, and we're trying to figure out how many grams of lithium. But the stoichiometric coefficients, the 2 and the 1 that aren't shown here, those relate the number of moles, right? Not mass, okay? So what we need to do is we need to figure out the number of moles of hydrogen. And I know that in 1 mole of hydrogen, I have 2.02 grams of hydrogen. Look, if we were to stop right there, we would just have the moles of hydrogen. But again, I need to convert that to moles of lithium because I'm looking for the mass of lithium. Where would I get a conversion factor to do that? From my balanced equation. Let me show you. I know that for every 1 mole of hydrogen, I consume 2 moles of lithium. Look at that beautiful thing. Look, there we go. So this conversion factor comes from balanced equation. And now I can determine the mass of my lithium. Look, moles of hydrogen cancel. Sorry, there we go. Anyhow, and I know that in every 1 mole of lithium, I go over to my periodic table, I look up lithium. It says element number 3, lithium, and it has a mass of 6.941 grams per mole. So I put that in, 6.941 grams of lithium in 1 mole of lithium. Look at this. Dimensional analysis is the most beautiful thing. All the units cancel, and we're left over with grams of lithium. You punch that in your calculator. 9.89 divided by 2.02, multiplied by 2, multiplied by 6.941, and you get 68.0 grams of lithium. There you have it, my friends. Look, there is nobody in this class, when you have a calculator, right? Everybody's allowed to bring a calculator into the exam with respondus. There's nobody that can't do these calculations. Division and division and multiplication. Everybody can do that. What's the challenging part? The challenging part of chemistry is reading the problem and getting to here, right? Knowing what to do. How do you develop those skills? Practice, practice, practice. Okay, we're going to switch gears and kind of stay in the same lane, but we're going to kind of add an extra component here, and we're going to look at what are called limiting reactant problems. Okay, see if you can follow me here. A limiting reagent is a reagent, right, which is the same thing as saying a reactant or a starting material, whatever you want to call it. The limiting reactant or the limiting reagent is the reactant or reagent that gets used up first in the reaction. Now, you might be thinking, like, why would one get used up first? Well, what if we had a vast excess of one over the other? Let me give you an example. Okay, this is the simplest example I can come up with off the top of my head. How do you make a hot dog? You have a hot dog and then you have a bun. Does that look like a hot dog? I don't know. There's your hot dog, okay? You need one bun plus one dog. Is that what you call a hot dog? To make a complete hot dog. Now let's say we had, 1, 2, 3, 4, 5, 6. We got 6 buns, okay? But we've only got, 1, 2, 3 hot dogs. Okay, 1, 2. We've only got 3 dogs. Okay, how many hot dogs can we make if one complete hot dog consists of one bun and one dog? Could anybody answer that? And it's not a trick question. Okay, yeah, thanks, Davey. The answer is 3, right? So which one of these is the limiting reagent? The answer is the dogs are, this is the limiting. All right, this would be the limiting reactant or limiting reagent, because the amount of hot dogs, complete hot dogs that you can make are limited by the amount of, I guess maybe it's actually called a wiener. I don't know. Anyhow, limited by the number of wieners you have, right? So there you go. You can only make 3 hot dogs and you got 3 buns left over. The same thing applies in chemistry. What if you only have a little bit of carbon monoxide, right? And you've got a lot of hydrogen, or vice versa. Well, one of them is going to get used up first. Let's take a look at what's going on here. You can see the little gray spheres here. These represent hydrogen. And then this one here, the black sphere and the red sphere, that represents carbon monoxide. So if you look at this cube over here, how many hydrogens do we have? We have a total of 1, 2, 3, 4, 5, 6. So we have 6 hydrogens. Okay, I'll just put the number 6 down there. How many carbon monoxides do we have? We have 1, 2, 3, 4. We have 4 carbon monoxides. But the problem is the ratio isn't 1 to 1 like the buns and the wieners, right? It's a little more complex. The ratio is 1 to 2. Okay? So even though we have more molecules of hydrogen, it is the limiting reactant, right? Because for every H2, every 2 H2s, I only consume 1 CO. Let me just draw it over here. If we tally it up, look, if we have a total of 6 H2, look, we have 2 H2s, right? And they're going to combine with 1 CO. That's okay. If we have 2 more H2s, they're going to combine with another carbon monoxide. If we have 2 more H2s, it's going to combine with another carbon monoxide. Look how many H2s we've used up. 1, 2, 3, 4, 5, 6. They're all gone. Okay, it's eliminated. How many carbon monoxides did we use up? 1, 2, 3. That means we're going to have 1 carbon monoxide left over. Okay, so hydrogen in this case is limiting. It's limiting the amount of this is methanol here. Methanol, okay. Anyhow, it's going to limit the amount of methanol that's formed, and carbon monoxide is the excess reagent. Give me a thumbs up if you just follow me on the concept. You're like, yeah, I get it, Mr. Dion. I have a whole bunch of one, and I don't have I don't have a whole lot of the other maybe. One of them's going to get used up first. You know, what my limiting reagent in life is? Money. Right? You guys wouldn't believe all the stuff I would do if I had the money, right? There's lots of things Mr. Dion would like. I'd own a few more cars, few more houses, few more vacations. Boy, oh boy. And the only thing stopping me from doing all those things is money. It's hard to believe, but that's the only thing standing in my way. So that's kind of a limiting reagent. Anyhow, maybe you'd say, limiting reagent in my life is time, right? Everybody seems to be limited by time. Anyhow, something to think about. All right, let's look at a problem. So this is example 3.15. We're going to go through the whole thing. I might even need some blank space, some Taylor Swift blank space to do this one. It says urea. So urea is actually found in urine. It's prepared by reacting ammonia with carbon dioxide. Here's the reaction. This NH3, that's ammonia. You're combining it with carbon dioxide. There. Here's your urea plus water. There we go. So it says, maybe I should erase all that. Anyhow, it says, what are you doing? You are taking 637.2, so you've got 637.2 grams of urea, and you're treating it with 1,142 grams of carbon dioxide, and it's asking you which one of these is the limiting reagent, and it's asking you how many grams of urea is formed, and then it asks you how much excess is left over. Okay, well, the first thing I notice is that we don't have a balanced equation, so we would want to do that first. I'll do it up here at the top, and probably some of you have done that, faster than me. You have your ammonia plus your carbon dioxide, and it's producing your urea. There we go, plus water. So if we want to balance that out, you notice that here we have 2 nitrogens, and here we only have 1. So I'll put a 2 there. Now on this side, we have a total of 6 hydrogens. Here we have 4 plus 2, that's 6. And here we have 1, 2 oxygens. Here we have 1, 2 oxygens. And we have 1 carbon and 1 carbon. There you go, my friends, balanced equation. That didn't take very long. Okay, so let's do some of the math here. And here's our strategy. We're starting out with, again, we have 637.2 grams of ammonia, and we have 1,142 grams of carbon dioxide. You're going to need a pencil and scratch paper to solve a problem like this on your exam. Why? Because you actually have to run 2 complete sets of equations or to figure out which one is the limiting reactant. So let me show you what I mean. What we're going to do first is we're going to pretend that we've got the 637.2 grams of ammonia, and we're just not even going to worry about the carbon dioxide. We're going to pretend like we've got all the carbon dioxide in the world, and we're going to figure out how many grams of urea we could make. Okay, so we're going to run that whole calculation set. Then we're going to do it again, except now we're going to do it with our 1,142 grams of carbon dioxide. We're going to figure out how many grams of urea we would get. We're going to ignore this completely. Whichever one of those numbers, those masses of urea, is the smallest, that tells you what is the limiting reactant. Okay, so let's start with our ammonia, and I'll try to color code it here. So we've got 637.2 grams of ammonia. I've gone ahead and calculated some of the molar masses here. I'll write them down here. Ammonia is 17.04 grams per mole. Urea, so NH2, 2CO, is 60.06 grams per mole. And CO2, which we looked at in the last problem, so I'll just scribble it down here. CO2 is 44.01 grams per mole. Okay, so let's finish our calculation. So we're starting out with 637.2 grams of ammonia. Let's figure out the number of moles of ammonia. I know that in 1 mole of ammonia, I have 17.04 grams of ammonia. I don't know why I keep writing NH2 like that. Okay. Now from my balanced equation, I know that for every 2 moles of ammonia, I form 1 mole of urea. So for every 2 moles of ammonia, I form 1 mole of urea, NH2, 2CO. And then I know that in 1 mole of urea, NH2, 2CO, it's got a mass of 60.06 grams of urea, NH2, 2CO. Just ran out of space there, but you can see that grams of ammonia cancel, moles of ammonia cancel, moles of urea cancel, and I'm left over with my mass of urea. And when I punch that all in my calculator, I get 1,123 grams of urea. I'll just write the word out like that. Now we're going to do that entire set of calculations, but we're going to do it for the carbon dioxide. Okay? Do the whole thing for the carbon dioxide. I'm just going to move this up here. So let's do it in blue, color code it. I'm starting it with 1,142 grams of carbon dioxide. I know that in 1 mole of carbon dioxide, I have 44.01 grams of carbon dioxide. From my balanced equation, I know that for every 1 mole of carbon dioxide, I form 1 mole of urea. So 1 mole of CO2 produces 1 mole of urea, NH2, 2CO. And again, I know that in 1 mole of urea, I have 60.06 grams of urea. And when I punch all that spinach into my calculator, look, mass of carbon dioxide cancels. The number of moles of carbon dioxide cancels. The number of moles of urea cancel. And I'm left over again with mass of urea, and I get 1,557 grams of urea. So here are my 2 possible yields. Could anybody tell me what is the limiting reactant in this situation, in this reaction? Is it the ammonia or the carbon dioxide? Yeah, it's the ammonia. So that way we know that ammonia is limiting reactant, like that. So ammonium is this. If you have NH4 plus, that's ammonium. That's something else. All right, there we go. So we did it. We figured out what the limiting reactant is. So we've solved part A, and it says calculate the mass of urea formed. We've already done that. We know that it's 1,123. That's the maximum amount we're going to make. So the next question is asking us, how much excess reagent is left over? So it's asking us, what's the excess reagent? That's the one that we've got too much of, right? And if ammonia is the limiting reactant, that tells us that we've got excess CO2, right? We've got too much CO2. Okay. Well, what are we going to do? What we're going to do is we're going to take the mass of ammonia. So I'm going to start over here. Okay, I'm going to balance my equation first. So here we go. I'm going to start with my mass of ammonia, which was 637.2 grams of ammonia. And since I know the ratio of ammonia to carbon dioxide is 2 to 1, I'm going to figure out exactly how much carbon dioxide was used up. Okay, so let's do that. So if we have our 637.2 grams of ammonia, and in 1 mole of ammonia, we have 17.04 grams of ammonia. And I know that for every 2 moles of ammonia, I produce 1 mole of CO2. And I know that in 1 mole of CO2, I've got 44.01 grams of CO2. So this is going to tell me exactly how much CO2 is used up, right? Because I know that this is going to limit the amount of CO2 that reacts. And so when we punch that in, we get, let's see here, we get 637.2 divided by 0.04 divided by 2 multiplied by 44.01. and we get 823 grams, 823 grams of CO2, okay? Used. This is what gets used up, right? That's what gets used up. But how much did we have that we started with? We started with this, right? So the amount of CO2, or the mass of CO2 remaining, okay, is going to equal what we started with, 1,142 grams, okay? Subtract what actually got used, and all that got used was 823 grams. And when we subtract that, we end up with 319 grams of CO2 remaining or left over, okay? And you could use that maybe for another reaction. All right, now if you're thinking, hey, Mr. Dion, that's going to take a long time for me to solve that. It's going to take a lot of paper to solve a problem like that. Yeah, it'll take you a piece of paper. Yeah, I solved it on one face of one sheet of paper. So yeah, that's why I recommend having a pencil, scratch paper. Give me a thumbs up if you follow me on the at least just the concept of limiting reactant. You're like, I get the concept, Mr. Dion. I might need to practice it. Good, thanks, Warren. Yeah, absolutely. I never expect, I'd be a lunatic if I thought, students would see this for the first time and be thinking they would, I understand everything about this in 5 minutes. No, it takes a little practice. But just go back to my example here with the buns and the wieners, right? It's the exact same concept. When would you run into this kind of concept in the real world? Well, I can tell you that I ran into this concept many times in my real life because I worked as a chemist most of my adult life. And there's many situations that you run into in a laboratory setting where, let's say, one reactant is really expensive and the other one is really cheap. Well, which one do you think you're going to use that's going to be the limiting one? Probably the one that's really expensive, right? You're only going to use a little bit of that because it costs a lot of money. So, those are the kind of things, kind of scenarios where you run into limiting reactant problems and you have to be able to solve for limiting reactants. Well, let's look at another problem here. This is question 3.16 or example 3.16. It's a lot of text in these problems. I have to give myself some blank space to solve them. Anyhow, it says the reaction between alcohols and halogen compounds to form ethers is an important reaction in organic chemistry. It's shown here. So we have methanol. This is methanol, which is wood alcohol. It can get you drunk, but it can kill you too. It can make you go blind. And methyl bromide, okay, to form dimethyl ether. That's this here, which is a useful precursor to other organic compounds. It's also a propellant. So if you think of an aerosol, like maybe whipped cream or something like that, it usually uses dimethyl ether as the propellant. The reaction is carried out in a dry organic solvent, and butylithium, that's this guy right here, serves to remove a hydrogen from the methanol. Butylithium will also react with any residual water in the solvent, so it's usually carried out with 2.5 molar equivalents of that reagent, just in case there's anything around, How many grams of methyl bromide and butylithium will be needed to carry out the preceding reaction with 10 grams of methanol? So let's start by writing out our equation. So I'm going to rewrite it up here. And in the interest of space, I'll try to, so I've got my, come on, I can do better than that. I've got my methanol, CH3OH, plus my methyl bromide, plus my butylithium, which produces my dimethyl ether, plus lithium bromide, plus butane. So this is C4H10. That's called butane. Same butane found in a butane lighter. Well, what it's asking us, it says if you have 10 grams, 10.0 grams of this guy, okay, how many grams of this do you need in your reaction? And how many grams of this do you need? Okay, Y grams, we'll call it. How many grams of both of these do you need? Well, again, we can't, and I'm repeating myself, okay, we can't compare masses directly. This is a balanced equation, okay, everything here is balanced. Everything here is balanced. I can't compare masses directly, can I? You could get in big trouble by doing that. But I can compare the quantities of moles. So that means I need to take this number, the 10 grams, convert it into number of moles, compare the number of moles of these two, figure out the number of moles of methyl bromide, and then I can figure out the number of grams from the molar mass, right? So that means I'm going to need the molar masses for all three of these in order to solve this problem. Now I've gone ahead and done the work already. I'll just write them down here. So methanol, CH3OH, I have to look carefully at my notes here, has a molar mass of 32.04 grams per mole. Okay, methyl bromide, CH3Br, has a molar mass of 94.94, so 94.94 grams per mole. And butyllithium, so lithium C4H9, has a molar mass of 64.05, so 64.05 grams per mole. And again, you would calculate those using the periodic table, right? You're going to have a periodic table on all of your exams, so you would just use that to solve, okay? What I'd like to do now is just to give you a minute to take a look at the problem yourself and see if you can at least start the problem, okay, without my help. So I'll give you, I don't know, I'll give you 1 minute to try and give it the old college try, and then we'll take a look at it as a group. All right, well, let's take a look at the first one. We're going to solve for the number of grams of methyl bromide that would be required. That's the CH3Br. So I'll do that in blue. Again, we're starting with our 10.0 grams of methanol, CH3OH. And I know that in 1 mole of methanol, CH3OH, I have 32.04 grams of methanol. If I was to stop right here, the mass of methanol would cancel, and all I'd be left over with is the number of moles of ethanol. But that's not what I want, is it? I want the number of grams of methyl bromide. So I need to find the relationship between the number of moles of methanol and the number of moles of methyl bromide. And then I see the ratio is 1 to 1. For every 1 mole of CH3OH, I consume 1 mole of CH3Br, like that. And then I know that in 1 mole of methyl bromide, CH3Br, I have 94.94 grams of CH3Br, like that. Look at this. The number of moles of methanol cancel, the number of moles of methyl bromide cancel. And I'm going to end up with the mass of methyl bromide. I'm going to check my calculation here before I write it down. So 10 divided by 32.04 times 94.94. And you end up with 29.6. So 29.6 grams of CH3Br is what you need. Okay, so we get that. Next, we're going to solve for the amount of mass of butyllithium. So we're going to start over. Same thing. We get our 10.0 grams of methanol. Okay, same conversion factor. For every 1 mole of methanol, I have 32.04 grams of methanol. Again, if we were to stop here, and don't stop there, but if we were to stop there, you'd just end up with the number of moles of methanol. But you see that the ratio is 1 to 1. But I just realized something, just thinking about the problem, Yeah, nobody stopped me. Good thing. It says here, yeah, it says the reaction is typically carried out with 2.5 molar equivalents, right? So if we have 1 to 1 here, that means here you need 2.5. And if you're thinking, Mr. Dion, that's not balanced. You're right, it's not balanced. They're saying you add extra, okay? That's what they're telling you. So we need to put 2.5. So again, even though the equation is balanced, they're saying in order to get it to work, for every 1 mole of methanol, you use 2.5 moles of butyllithium. And I know that in 1 mole of butyllithium, C4, come on, C4H9, I have my molar mass, which was 64.05 grams of butyllithium, like that. So let's see here, moles of methanol cancel, moles of butyllithium, and we're left over with the mass of butyllithium. Let me double check that one too. So I have 10 times 64.05. And I end up with 50.0 grams of butyllithium. Okay, if you think about cooking, you know, if you go to the cupboard, you want to make chocolate chip cookies maybe, and you say, well, I've got this much flour. Well, I don't know how to make chocolate chip cookies, but, you know, based off of how much flour, maybe that will dictate how many chocolate chips you can use and how much sugar you can use. So it's the same rationale. We're limited by the amount of methanol that we have. So if we want to put everything together and not waste reagents or reactants for nothing, we've got to have the proper amounts of everything. All right. Give me a thumbs up if you follow me on that one. You're like, you know what? I think I'm getting it. Okay. All right. Well, let's look at the last 2 slides and that'll finish the whole chapter. The next thing is, you guys remember reality TV? I don't know. I'm too old to know. Is that still a thing? But it used to be a big thing, you know, reality TV. And whenever I see this slide, whenever a chemist sees any slide that says reaction yield, all you can think of is reality, you know, the harsh reality of life, okay? Because everything that we've looked at up till this point dealt with theoretical yields. Theoretical yield is not reality, right? The theoretical yield is the amount of product that would result if the limiting reagent, if all the limiting reagent reacted. So that would be ideally, okay? If everything in a perfect world, it all reacted perfect, you know, and you got no other problems, no side reactions or anything like that. That's what you would get. Actual yield, this is reality. So theoretical, what we call that in your dreams, an actual yield, this is reality. Okay. And the way that we calculate our percent yield is we take what we get, our actual yield, we divide it by what we hoped to get, the theoretical yield, if all the limiting reagent reacted, we multiply it by 100%. Okay. I worked a long time as a chemist. I can't tell you how many times, you know, I was hoping to get a 90% yield on something. Like, let's say I wanted to make, you know, 9 grams of something. So I designed a reaction that was going to make 10 grams, and I assumed I was going to end up with 9 grams. I multiply that by 100, and I get 90%. Hey, that's pretty good, right? But then I'd go into my boss's office and I'd say, boss, you know, it ended up being more like this, you know, 2.5 grams, and I get a 25% yield, right? And then you kind of feel like this for the rest of the day, right? So that's what a reaction yield is, and you need to know how to calculate reaction yield. Let's look at this reaction quickly. It says here, titanium is strong, lightweight, corrosion-resistant metal that is used in rockets, aircraft, jet engines, and bicycle frames. It is prepared by the reaction of titanium 4 chloride with molten magnesium. Between 950 and 1150 degrees Celsius, a certain industrial operation uses 3.54 times 10 to the 7 grams of titanium 4 chloride reacting with this much magnesium, and it says calculate the theoretical yield of titanium in grams. And so this is turning into another limiting reactant problem, right? We have our equation, which is balanced for us, our titanium 4 chloride plus our 2 magnesiums produce titanium plus 2 magnesium chloride like this. right? They tell us the mass of the titanium 4 chloride. They tell us that it's 3.54 times 10 to the power of 7 grams. And they tell us that the mass of the magnesium is 1.13 times 10 to the power of 7 grams, like that. And what they're asking us is, what's the theoretical yield, right? What's the mass of grams of titanium that you would get? Well, this is a limiting reactant problem. What you need to do first is use the mass of titanium 4 chloride and figure out how much titanium you would get, right? Then you're going to do it with the magnesium, same thing, and figure out how much titanium you would get. Whichever one gives you the least, that's going to be the theoretical yield, okay? Because you can't have more than you would get from the limiting reactant, okay? Then you're going to calculate the percent yield if you ended up with that many grams actually obtained. All right, now in the interest of time, I'm going to stop here and I will make a video that I'll post to my YouTube channel where I solve this problem. Or we could look at it, let me think here, what's today? Today's Tuesday. Actually, we could look at it on Thursday night. So what I would like everybody to do before class on Thursday, I'd like everybody to, at a minimum, solve this problem. In fact, if you could solve a few more problems, that would be great. And maybe on Thursday night, we could look at a few more examples as well. All right, there we go.